All right, you guys, 5.3c, conditional probability and independence. So there are two ways to check for independence. One is to just think about it, and the other is the formula. Sometimes you have to do the formula. You can't just think about it, all right? So first of all, two events, A and B, are independent if the occurrence of one event does not change the probability that the other event will happen. That's like the think about it way, all right? And then we have the formula, which says the probability of A given B is equal to the probability of A given not B is equal to the probability of A. Remember, this has a formula. Just a reminder that the probability of A given B is equal to the probability of A and B divided by the probability of B. Okay? So remember, just a reminder that your conditional formula is always divided by the second thing. Okay? Your independence formula is always equal to the first thing. Okay? This independence formula is not on the exam sheet. You have to know this, all right? So this formula will not be given to you. So in order to check for independence, you do have to memorize this formula. So suppose you toss a fair coin twice. Define the events. A, first toss is ahead. B, second toss is ahead. What is the probability of B given A? So B is second toss is ahead, given A, first toss is ahead. What's the probability the second toss is ahead if we know the first toss is ahead? It is 1/2. Does it matter what the first toss was? No. Does not matter what the first toss was, right? All right. What's probability of B given not A? So in other words, what's probability the second toss is a heads, given that the first toss is not a heads, so it was a tails if it was not a heads. What's probability the second toss is a heads, you guys? Still 1/2. Doesn't matter what we got on the first toss. And what's the probability of B, which is second toss is a heads? 1/2. Are these events independent? Yes, if they are all equal, they are independent. Could we have just thought through this one? Yeah, right? So flipping a coin, those are definitely independent events. The first flip does not affect the second flip, okay? Here's one where you cannot just think through it. Back to our pierced ears gender example, all right? Are the events pierced ears and male independent? That's what we're checking for. You can go in either order, your pierced ears and your male, whatever order you want, as long as then you follow with the formula, right? And so if you put pierced ears first, then you got to do pierced ears at the end. So anyways, this says, what's the probability that someone has pierced ears given that they're male? So we isolate Kane, which column or row? Exactly. So Logan, what's the probability of pierced ears out of just the males? Okay. Then we're going to check the probability of pierced ears given not males. So Julia, if you're not a male, what are you? Yeah. So Sulav, what is the probability of pierced ears given not male? Yep. So it's the pierced ears out of just the females, 84 out of 88. Are those two fractions going to be equal? No. So I already know they're not independent, but let's check the last part, probability of just pierced ears. So Cam, what's the probability of having pierced ears out of everybody? Okay, what'd you say? Yeah, 103 out of 178. So none of these are equal. So these are not independent events. In other words, what do we know if we know someone is a male? We know they are less likely to have pierced ears. All right. So knowing that the chosen student is male changes or greatly reduces the probability that the student has a pierced ear. So the two events are not independent. Knowing one does affect the other one. All right. Let's try another one. Is there a relationship between gender and handedness? To find out, we use Census at Schools random data selector to choose an SRS of 100 Australian high school students who completed a survey. The two-way table displays data on the gender and dominant hand of each student. Are the events male and left-handed independent? So this is how I'd like you to set it up, all right? It actually does not matter what order you put these in, all right? But let's write it like this. Probability of male given left-handed equals the probability of male given not left-handed equals the probability of male. So I kind of prefer you go across and then you show your three fractions underneath there and if they're equal, okay? So probability of male given left hand. So Cassidy, what would be, Cassidy C, what's the fraction for probability of male given left-handedness? Yeah. So this is the row or column that you isolate, you guys. The second one when you're doing these conditionals. And so I have 7 males out of 10 who are left-handed. Now I have the probability of male given not left-handed. So Eve, if they're not left-handed, what are they? Good. So Kendra, what's the probability of being male given that they're right-handed? Good. 39 out of 90. I can already tell those are not going to be equal. And then we have the probability of male. So Aaron, what's the probability of just being a male? Yep, look at that whole total, 46 out of 100. Okay, none of these are equal, so you should put some little slash marks in there. And if they are not equal, they are not independent. Okay, we could have also gone this way. Probability of left-handed given male. And you can skip this middle step if you want to. If I go this way, what am I going to set it equal to, you guys? Exactly. You always do the first thing, okay? You are allowed to just check this for independence, and that's how your book does it, all right, is just this. So let's say I did it this way. Probability of being left-handed given that they're male. So Aaron, what's the probability of being left-handed given that they're male? Actually, just calling you Luke. What's the probability that they're left-handed given that they're male? Okay, good. Now we go this way. So 7 out of 46 equals probability of being left-handed out of everybody. And so Sam, what's the probability of being left-handed out of everybody? Yep, 10 out of 100. Okay, not equal, so not independent. You will get the same answer whichever way you go. Make sense, you guys? All right, for each chance process below, determine whether the events are independent. Justify your answer. Shuffle a standard deck of cards and turn over the top card. Put it back in the deck, shuffle again, and turn over the top card. So I'm replacing cards. Define the event. The first card is a heart, and B, the second card is a heart. So we're going to check our formula. Probability, and again, it doesn't matter what order you go, so I'll say first card is a heart, given second card is a heart. And I'm going to check, is that equal to the probability that the first card is a heart, given that the second card is not a heart? And then check, does that equal the probability the first card's a heart? How many? Yeah, you can. Yep. How many cards are hearts, you guys? 13. It's a whole suit, right? So it's a fourth of the deck. Now, what's the probability the first card's a heart, given that the second card is a heart, when you replace it? This is 13 out of 52. Okay, what's the probability the first card is a heart, given the second card is not a heart, and when you replace it? Still 13 out of 52. And what's the probability the first card's a heart, if that's all you're asking? 13 out of 52. Are these independent? Yes. Okay, these are independent events. Did I even need to do any of the formula? No, because you're replacing cards, right? So that means that the first draw does not affect the second draw, as long as you replace the first card back into the deck. So you could show the work, or you could say independent, because we are replacing cards. Knowing what the first card was will not help us predict what the second card will be. All right, now we're going to shuffle a deck of cards and turn over the top two. So we are not replacing, one at a time. First card's a heart, second card's a heart. So right off the bat, if we are not replacing, are these independent? No. So I already know, because I'm not replacing, that these are not independent events. Does the first draw affect the second draw? Yes, right? Whatever I get first changes the fraction on the second one, right? And I could go through that formula, and you would know that your second draw for hearts would be 12 out of 51 if you got a hearts on the first draw. So it does change it. So those are not independent events. 28 students in Mr. Tabor's AP Stats class completed a brief survey. One of the questions asked whether each student was right or left-handed. The two-way table summarizes the class data. Choose a student from the class at random. The events of interest are female and right-handed. Are they independent? So I want you guys to do this one on your paper. So are the events female and independent, or female and right-handed independent? And they're missing some totals on this that you might want to find. All right, so Fia, how'd you set up your just formula? Okay, I ran out of room. Great, okay. So let's start with the probability of female given left-handed. And Allison, what would you get for the probability of female given left-handed? Okay. And the probability of female given not left-handed. So Addie, what would you get for that guy? Good, 18 out of 24. So we had 24 here, we had 4 here, which meant there were 28 total. All right, and then we need just the probability of being female. So Abby, what's the probability of being female? Yep, 21 out of 28. What do all those fractions reduce to? Some good old-fashioned mathematics right here. Okay, yep, or just divide on your calculator and get the decimal of 0.75 on all of those. And so are these independent? Yes. Could you have gone the other way and done this? Yes, right? So you could have gone the other way too.